So we'll focus just on drawing a rotated stress state at a prescribed angle here, 40 degrees counterclockwise rotation. So there's our initial state of stress. In tensor notation, of course, we would need a coordinate system xy. So if we wanted to put this into the tensor, it would be minus 5.93 and 0. It would be on the x face in the positive y direction, so it would be plus 1.37 plus 1.37. So there would be our matrix. Right? Counterclockwise would be creating a positive, so it would be theta is equal to positive 40 degrees. And we can go ahead and run the equations, right? Either in equation format or matrix format. And that would end up getting us out the answers for the state of stress at that rotated amount. So on Moore's circle, let's take a look at the graphical solution. So we need our 2 points x and y. So on the x face, we've got minus 5.93 normal. On the y face, there is no normal stress. On the x face, right, shear stress. On the positive x face, the shear stress would be causing rotation in the counterclockwise direction. And sometimes I should do this first. I like to come down here and just put our axes. And that reminds me the exact sign convention for shear stress. So I can go back up here, and that would be minus 1.37. This would be plus 1.37. So what we're going to do is plot those 2 points and start to make our circle. So these points here would be at, we're going to make sure we have a decent scale going. So we'll go 2, 4, 6, 8, 2, 4, 2, 4, 2, 4, minus 4. So that gives us a chance to actually end up with a circle. So minus about 6. That's 2, so we end up with a point about right here for x. Our y point will be sitting about right here. And I like to sometimes put the coordinates right there, minus 5.93 minus 1.37. Y point 0, comma, plus 1.37. So there is our initial stress state. So we would be able to figure out the radius and the center. So I'm just going to kind of skip a step or two, but just calculating it, but we get minus 2.97 for the center. We'd end up with an R. R would equal 3.27. Good to have yourself check on that. And I'm going to highlight the pink theta right here. So that angle theta is one that we know. And so we'd be able to calculate it. So the tangent of the pink theta would equal 1.37 divided by 2.97. So it would give us an angle of the pink theta of 24.8 degrees. So I'm just going to put 24.8 degrees right there. All right, and what we're called to do in this problem is to rotate 40 degrees counterclockwise, which on Moore's circle would be 80 degrees. So we're going to take those points and we are going to strike them to some location through approximately 80 degrees. And we would end up with a state of stress right there. All right, so that's just part of our Moore's circle rotation. And so this becomes a geometry issue, and we want to find the coordinates of these points. So one way to do that would be to highlight this triangle right there. And so we would have another angle theta. So our theta games would tell us that 90 plus the red theta right there would have to equal the 80-degree rotation plus the pink theta, the 24.8 degrees. So if we go ahead and solve for that, we would see that theta is 14.8 degrees. So I'm just going to draw this triangle right over here, nice and big. That is not on the coordinate system, but it has a side R. It has a 14.8 degree. And up here, it would be sitting at sigma equals minus 2.97. And so we'll have the little bit of simple trig to solve for L1 and L2. We'll be able to do that using sines and cosines. So the sine of 14.8 degrees is equal to L2 over R, and we've got R from our previous calculation. So doing the math, L2 is equal to 0.835. We'd also be able to find that L1 is equal to 3.16. So I'm just going to write those on here. That's equal to 0.835, and that's equal to 3.16. So again, what we want is the coordinates. We want the location of that point, right? The x prime spot. So the coordinates, right? The coordinates of those points would end up being, for the x prime, that would equal minus 2.97, right? Which is where the top of the triangle is sitting on the horizontal axis. And I'm going to add to it 0.835. For the shear stress, it would be sitting, excuse me, at negative minus 3.16, right? Looking back here, right? It's on the negative side of the, or on the bottom side of the horizontal axis. So let's go to do our math. That would be minus 2.135 and minus 3.16. Right? And whether or not we realize it also, right, that y prime point has been defined. And so we would know the shear stress is going to be the negative of what we found above. But the normal stress would be minus 2.97 minus 0.835. Let's kind of look here. There's the center at minus 2.97. We would go back the distance L2. So we would subtract 0.835 from it. So the total location would be minus 0.381 plus 3.16. So our element now would be sitting at 40 degrees, excuse me. So we rotated it 40 degrees. That would be the x prime. That would be the y prime axis. Right? Again, originally it was x, y. Right, we went counterclockwise, so now the x prime is sitting up in the air, and all we're going to do is just draw the answer on. So the x prime face has compression, 2.135. Y prime face also has compression. It's bigger compression, 3.81. Shear stress is negative on the x prime face. Negative is going to be counterclockwise. So down here I'm going to draw a shear stress that would cause the element to rotate in a counterclockwise direction. If I can draw one, I can draw all four. 3.16. So there's the rotated state of stress.